What's up, mathematicians? Justin here, and in this lesson we'll be looking at bisecting. Now, if you recall, in the last lesson we talked about the rules, we looked at the axiomatic system we're working in, and we went through our first few proofs. Now, the rest of this unit will continue to be fairly proof heavy. Not all the lessons will involve proofs, but most of them will. And if you're just here for the constructions and not the proofs, though I don't know why you would be. I mean, proofs are the good part, right? But anyway, this video and many of the subsequent videos will have a construction in the first few minutes, and then it'll be followed by a proof. So you could just watch the construction part and then skip the proof. I mean, do you really want to do that? But I don't know why you would, because you'd be missing out, because the proofs, that's the good part. That's the real, getting into the meat of the mathematics of what we're doing. But anyway, just to let you know. So before we get into the bisecting constructions, what does it mean to bisect? Well, to bisect just means to divide in half, or to divide into two equal parts. We're going to start with the angle. So how to bisect an angle. The first thing we need to do is we need to have an angle. So let's go ahead and draw an angle. And in order to do this, I'm just going to draw 3 points on my sheet of paper here. And then we'll draw out an angle. Okay. So there we have an angle. Now, before I actually do the bisection construction, I encourage you to try it out on your own. See if you can come up with a way to divide this angle into two equal parts, two equal angles on your own. Pause the video and give it a shot. All right, welcome back. I'm going to show you two methods for constructing the bisector of an angle. The first method involves creating an equilateral triangle. So first thing we're going to do is we're going to take our compass and we're going to set it to some width. It doesn't matter too much what the width is. Don't make it too small, but also don't, it'll be limited by whatever size your angle is and whatever size your compass paper is. So a reasonably long length. So I'm going to set it to be there. Okay. Now I'm going to draw an arc across the angle from this point right here. Okay, so now that I have my arc, I'm going to go ahead and draw a line connecting these two intersection points. And now that I have this line, I'm going to draw an equilateral triangle. I'm going to construct an equilateral triangle on this line. So I'm going to construct it moving, so the point is away from the point of the angle. So we talked about the construction of the equilateral triangle in the last video. If you didn't catch it, then you can go back and watch that. So I have here my third point of the equilateral triangle, and let's go ahead and draw these lines here. Okay, and now in order to draw a bisector, I'm just going to connect this point on the equilateral triangle with this point right here. So I'm going to draw a line from here, just going out like that. And now this angle right over here is equal to this angle right over here. This line is the angle bisector. So that's one method for bisecting an angle. The second method, and probably the more typical construction that you'll see, is not based on an equilateral triangle, but based on a rhombus. And so in order to do this, we're going to start by drawing an angle once again. So let's go ahead and draw out my angle. And once again, I'm going to set my compass to be, whatever length, not too long, not too short, and draw an arc across here. Now what I'm going to do is I'm going to actually keep my compass the same width, and I'm going to move to the two intersection points and draw more arcs across the angle. So one here. I'll move to the other intersection point. And there it is. So then I will go ahead and put a point there, define a point at that intersection, and take my straight edge and draw a line. So once again, this angle right here equal to this angle right here. And I've bisected the angle. Okay, now that we have finished with the construction of the angle bisector, we're going to move on to the proof. Now, as you recall, I showed you two different constructions. This one is based, the first one, based on an equilateral triangle, and the second based on a rhombus. Basically, if you connected these points and these points, you'd end up with a rhombus. I'm going to base my proof on the first one, the equilateral triangle construction. So in order to prove something, we need to start out by knowing what we're given. So in this case, what are we given? We're given an angle, and let's actually define some points on this angle so that we can label it properly. So I'm going to call this point A, this point B, and this point C. So given angle A, B, oops, no, I labeled it incorrectly. Sorry about that. So A is in the middle, so it's going to be angle B, A, C. Okay, so given some angle, BAC, our goal is to bisect this angle, bisect angle BAC. Okay, so step one, we're going to draw a circle centered at A. Now, I'm not going to specify the radius of the circle. I could specify it to be AB or AC or something like that, but I'm not going to specify it because the rules say that I can draw a circle centered at any point with whatever radius I want. So my justification here for drawing a circle centered at A is rule 1. I'm just going to abbreviate this as R. Oh, no, sorry. It's not rule 1, it's rule 4. Let me correct that. So R4. And let's go ahead and do it. So I'm going to center the compass at A. And I won't draw the entire circle, but there you go. And then step 2, I'm going to define the points. And let's see, I've got A, B, and C, so I'll define these points as D and E. So define points D and E at the intersections, basically the intersections between the circle and the angle. Now, rule number 1, I'll abbreviate R1, says that I can draw or define a point anywhere in my space, on my sheet of paper. So that's my justification for that. Okay, so now I am going to rely on one of the proofs, one of the constructions from the last lesson. Step 3 is going to be construct the equilateral triangle DEF. Using these points D and E, and then the last point on the equilateral triangle be F. So what is my justification for this? Well, now I'm not justifying this based on the rules, I'm justifying it based on a brick. And it's this brick right here that I can construct an equilateral triangle. So I'm going to abbreviate that as B2, brick number 2. Let's go ahead and do it. So I'll draw my arcs here. Let's make sure that my compass is the right width first. Okay. So go ahead and draw that arc there. And go ahead and draw this arc right here. Okay. So now this is going to be point F. And let's go ahead and draw in this equilateral triangle. Okay, so that was step 3. Now, as you recall from the construction, the bisector was the line that I draw from A to F. Let's go ahead and draw that line in here, and then we'll add the step to our proof. So there's the line. And so step 4 is going to be draw AF. And the rule that says I can draw this line is, let's see, rule number 2 says I can connect 2 points with a line. So draw AF. That is rule 2. I'll abbreviate it as R2. All right, now let's look at the situation. We want to prove that this angle here is equal to this angle here. Well, if I could prove that this triangle ADF was equal to the triangle AEF, it would seem to follow that these two angles were equal. If the triangles are equal, the angles should be equal, right? That makes sense. Should make sense, I think. And so how could we do that? Well, if we look at our rules, I don't see anything here about triangles being equal. I don't see any bricks here about triangles being equal. So we might have to just strike out on our own a little bit and see if anything comes to us. Well, first of all, a couple things that I notice is that this line here equals this line here. And let's go ahead and write that down. So DF is equal to EF. Our justification for that is the fact that this is an equilateral triangle. Since it's equilateral, all the sides must be equal. So I'm going to say the definition of equilateral triangle. Okay, now let's look at the diagram again. Well, I notice that this length AD is equal to the length AE. Okay. And what is our justification for that? Well, they're defined based on the points of a circle centered at A. And so AB is equal to, sorry, not AB, AD is equal to AE. And that is the definition of a circle. Because these 2 points are on a circle centered at A, these lengths are equal. Okay, so now if I look at it, I can say this length AF, I mean, that's part of both of those triangles, ADF and AEF. Well, AF is, you know, equal to itself, right? It must be. So what that means is that the sides of ADF, all 3 of them, are equal to the corresponding sides in ACF. This side is equal to this side is equal to this side, and this side is equal to itself. So does it seem clear or obvious to you that if 2 triangles have all 3 sides equal, those 2 triangles must be equal? Now, this is something we could debate about. Now, if we're going to be completely honest, though, it's not logically necessary that just because the 3 sides are equal, the two triangles have to be equal. It's not logically necessary, but it sure seems like it should be true. Let's go ahead and say that, let's go ahead and state it. So we'll say triangle ADF is equal to triangle AEF. Now, how would we justify this? We could say it's obvious. Maybe it seems obvious, but it doesn't seem quite as self-evident as saying, like, if A equals B and B equals C, then A equals C. We can say our intuition tells us it should be right, but our intuition can be off, and we talked about that in the first unit. Really, we should have either an assumption or a theorem to back this up. Since I haven't proven a theorem, I'm going to add this to our list of assumptions. So you notice I put other assumptions here and I left it blank. So I'm going to put the assumption S, S, S. This stands for side, side, side. Basically, if the three corresponding sides of one triangle are equal to the three corresponding sides of another triangle, the two triangles are equal. I haven't proven it. I'm adding as an assumption, and you may or may not like that fact, that you may think, like, shouldn't we try to prove it first? We will revisit this question later in the course, in the next unit, but for now we're just going to go ahead and say, well, we don't have a proof for it, so we're going to add it to our assumptions. Okay, so now that I know that these two triangles are equal, I'm going to go ahead and state that those two angles must be equal. So step 8 is that DAF angle DAF is equal to angle EAF. Once again, because the two triangles are equal by side, 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 those two angles are equal. So I'm going to use side, side, side to justify that. And finally, step 9, AF, the line AF bisects the angle BAC. And that's by the definition of bisector. Okay, this line AF divides the angle into two equal parts, and that's our definition for bisector. So we're done. Mathematicians have this sort of tradition when they finish a proof of sort of signing it, indicating that it's done by writing QED, which comes from Latin. It's based on the Latin for, I don't remember the exact phrase, but but translated it means which was the thing to have been proven. And that's exactly what happened. What was the thing? What was our goal that we wanted to prove? We wanted to prove that it's possible to bisect the angle. And turns out AF bisects the angle. So we did the thing we wanted to do. Okay, so let's go ahead and add a brick before we wrap up this video. So if you'll notice, we used the definition, or sorry, where is it? We used the brick. We used brick number 2, the construction of the equilateral triangle in this proof. So this proof depends on the construction of the equilateral triangle. So I'm going to build it on top of there. So let's go ahead and say, and this will be brick number 3, the angle bisector. Okay, so there we have one more brick in our system, which is great because we're building up, and we hope to get to the angle sum of a triangle eventually. So let's see, that's it for this video. In the next video, we'll continue this lesson by looking at the construction and proof for a line bisector. And thanks for watching, and we'll see you then.